Hello again. Let's consider the function from the closed interval -5 to 6 into the reals such that f of x equals x squared. We've got a continuous function such that the domain is a closed interval. The extreme value theorem will apply. So because continuous function closed interval for a domain. Observe that f of x is greater than f of 0 for all non-zero x. So aka for all x in the non-zero reals. As such, f has an absolute minimum and local minimum for that matter at x equals 0. But now we have endpoints to check. Remember, there is no local max. And there didn't used to be a global max back when the domain was all reals. But now we have a closed, bounded domain. Now there's still not going to be a local max. But there will be a absolute max. And guys, give me permission to do something. Back in the old days, some people call absolute max a global max. I may have a slip of the tongue and refer to absolute maximum as global maximum and an absolute minimum as a global minimum. Forgive me if I do that, but you'll know what it means if I do it, okay? Absolute is better probably, or maybe a little more in style, but some authors may use global. Absolute and global mean the same thing. So if I say global, I mean absolute. I don't mean local. Okay, local has its own meaning, okay? Another word for local is relative. Relative and local go together. Absolute and global go together. They're synonyms is what you call them, okay? But anyway, if you catch me, if I slip of the tongue and do that, if I slip the tongue, I'll try not to, but if I do, forgive me. But you'll know what I mean, okay? I don't think I've done that yet. I've tried to watch myself. But anyway, now, as far as we're never going to have a local max because if we didn't have a local max up here, we're not going to have one down here either, okay? Remember, we did f prime. F prime will always be defined, and f prime only equals 0 when x equals 0, but that's a minimum, so we're doomed as far as ever having a local max goes. You know, f prime equals 0 only at x equals 0, but that was a min. We do have a local min, but we're never going to have a local maximum. But we will have a global maximum, absolute maximum. There, I did it. So we'll have an absolute maximum. Okay. So, well, it would have to occur at the endpoints. Remember, we don't allow endpoints to be local, okay? Now, here's the deal. Let's check the endpoints. Let's plug the endpoints into the function. F of -5 is positive 25. F of 6 is 36. But we know that F increases as x gets bigger and bigger in either the negative or positive sense. Hence, F has an absolute maximum at 6. Because the reason why that is because f of 6 is 36, whereas f of -5 is only 25. F of -5 got beat by f of 6. Okay. That's what I'm saying there, okay? Now, so hence my absolute maximum is at x. It is located at x equals 6, and it is 36. Now, your professor might well ask you, what is your absolute maximum? It is y equals 36, aka f of 6 is 36. So that's y. That's a y coordinate. So your absolute maximum is y equals 36. Notice that's a y coordinate, 36. That is your absolute maximum. Now, where is it located? It is located at x equals 6. And you can do a similar exercise for local stuff too. What is your local max or local min? We don't have a local max in this problem, but in another problem, if you did have one, what is it and where is it. Like, what is it would be, what is it, like y equals something something, and where is it, x equals something something, okay? If if you had one in the first place, if you even had one at all. Okay. But anyway, now remember, the local, for minimum, we have y equals 0 is both our local and absolute minimum. Now, it is located at x equals 0. So there's that. Y equals 0 is our local and absolute minimum, and it is located at x equals 0. So y equals 0, our local and absolute min, is located at x equals 0. That's true for this one and the one we just did. Or the one we did in times past, that is, I should say. We might have did that other one on the last video, actually. I think we did that. Yeah, I think it was on the previous video we did that other one. But anyway, moving on. Consider the function f from -5 to positive 5 into the reals again, such that f of x equals x squared. Now, the only thing different that's going to happen, I won't go all the way through this. F of -5 and f of 5 both equal 25. 25 is our absolute max. It's not a local, though. So our absolute max is 25, or y equals 25, that is our absolute max. Now, it occurs in two places. It occurs at both x equals 5 and at x equals -5. So there's at x equals -5 and x equals +5, it occurs. Now, absolute max can occur at several different places depending on the problem. It might occur at just one place or two places or several, if you have one, But anyway, and the extreme value theorem did apply. We had a continuous function, a closed interval, all that good stuff. Now here, we got a continuous function, but we don't have the closed interval. Now, we still get lucky as far as 0 goes. We still have a local and absolute min at 0. We still got lucky there. But we have no maxima of any kind. Notice that -5, we want a -5 and 5, we're so close to having them, but we don't have them. They're outside our domain. So notice that we get indefinitely close to -5, and on the other side we get indefinitely close to +5, but we never get there. So, for any value we choose in the domain, let's say 4.999, I can go just a little bit higher and choose a number that will give me something a little bit better. But for that number, I can choose something that will give me a little bit better, because I can never get to 5. So I don't have an x value that will give me that, that maxima right here that I desire. I'm out of luck. Now you're like, well, Jason, did you violate the extreme value theorem? No, I did not, because this is not a closed interval right here. It's remember the extreme value theorem. Part of the stipulation, we had the finite closed interval. It had to be finite. It had to be closed. Now let's consider this guy right here. Consider the function from -1 to 1 such that f of x is the sine of x. Now here we go. Extreme will apply this time, the extreme value theorem, that is. Now this, wait, no. Back up. Broadway bites tongue. Broadway bites, I bite my tongue. No. -1 to 1 would have to be my domain for it to apply. The extreme value theorem doesn't necessarily apply here because the R is not bounded. Sorry, my bad. But we might still get lucky, even though the extreme value theorem doesn't, promise us anything. Just because the extreme value theorem doesn't make any promises doesn't necessarily mean that we won't get lucky. We still actually, as it turns out, what happens? We get infinitely many. And they're all the local and absolute extrema, they're all identical. And we have infinitely many. They're all the same. If you're the local and absolute extrema, they're all like a local, all your local maxim. Well, no, I need to watch what I say. in the sense, or well, I don't mean it like that. No, I don't. Let me back up. Here's what. Well, I don't mean it. All local max. Or all local max, and I didn't mean it like that, guys. I'm sorry. All local max and global max, or absolute. I'm sorry, or absolute max, are the same. And that's what I meant in the first place. I'm sorry. And then ditto for min. So all your local and absolute max are the same. They're the same. And likewise for your minima. That's all I was saying in the first place. I didn't mean that your min and max are the same. No. I didn't mean that. Like your minima are different than your maxima. Okay. Sorry if I came off that way. Okay. There's infinitely many. Okay. So now the minima by trigonometry, the minima occur for integer n. The minima occur at 4n plus 1 over 2. That's by the nature of the sine function. And the maxima occur at 4n minus 1 over 2. Okay. And again, guys, sorry about getting a little bit clumsy there. Yeah, I got a little clumsy there. Sorry. My bad. Yeah. But anyway. Yeah. I need to be careful. But yeah. But that's nice. So this is we have minima occurring. The minima occur here, and the maxima occur here. We know that. Yikes! Did I forget my pi? I sure did, didn't I? Did I forget my pi symbol? I want you to look. Yeah. Oops. I forgot my pi symbol down here too, didn't I? Yikes. Well. Yeah, that's not very valuable. It's not worth a dime if I don't put my pi symbol there. Okay. So yeah, that pi is understood to be in the numerator here, and likewise this one's in this numerator here. I forgot my pi symbol. My bad. So let me save that in the editing. So yeah. So pi halves should be here. So if I let n equal, let's say 1, I would get 3 pi halves. Well, no, that doesn't feel good. I think that should be min. Now I'm getting all crazy and all loopy. Sorry about that, guys. I must have. Sometimes when I type this, I need to be more careful, and I do apologize about that. It's 3. Oh. No. Actually, no. This is right. I know what I did wrong. Forgive me, guys. I had it right. Maxima does go here, and minima does go here. I just need to be, and 3 goes here as well. Those 1s should be 3s. And I'll save that in the editing as well. My bad. Okay. I knew something didn't feel right. I forgot my pi's, and those 1s should be 3s. Okay. All good. And that is correct. Okay. So the minima really do occur here, and the maxima really do occur here. And I'm sorry, 1,000 apologies for messing these up, but I've corrected them now. So, good deal. All right. Let's notice that just because the extreme value theorem doesn't promise something doesn't necessarily mean it won't happen. It's just not promised. Okay. And again, consider the function from the non-zero reals to the reals such that f of x equals 1 over x. F has neither min nor max of any kind. Be careful. Yes, f prime of 0 is undefined. But 0 is not a critical point of f because it's not even in the domain of f. Guys, f of 0 is not defined either. F of 0 must be defined. F of 0, that's bad. F of 0 not being defined is bad. Yeah, f prime is undefined, that's good. F of 0 being undefined is bad. Okay. Consider the function from the reals to the reals such that f of x equals 1 over x for x not equal to 0. And let's just put an inelegant patch. Let's just define f of 0 equals 1 for all the good it'll do, which isn't much. Then f still has neither min nor max of any kind. Yeah, f of 0 is defined, but f does not have a min or max at 0. If epsilon is some positive number, then f of negative epsilon will be a negative number, namely negative 1 over epsilon by this definition up here, whereas f of positive epsilon will equal this number by the same definition. And so anybody to the left of 0 will be negative, anybody to the immediate right of 0 will be positive. So 0 is neither a min nor a max, and the party is spoiled for x equals 0. And the same thing is true of any function of the type x to the negative p, which is 1 over x to the p. Like if this was 1 over x cubed right here, for example, okay? But anyway, guys, and again, this is 1 over x squared. A similar thing is going to happen to you. You're going to run out of luck. Let me continue this on the next video, guys. Let me do this example in the next video. I'm out of time and I gotta go. I'll see you on the next video. Bye-bye.